May I introduce myself? My name is Bablu Kumar Ghosh. I am senior lecturer from Faculty of Engineering, University Malaysia Sabah. Today I am going to present before you the hot and issue among the problems in the universe as the global warming and climate change issue. That how to mitigate the global warming or climate change issues using the renewable energy like solar photovoltaic. And the global warming SPV, the ultimate carbon-free energy prospect that I am going to present before you. So, thank you. So, the global warming, solar photovoltaic, the ultimate carbon-free energy prospects, represented by myself, Bablu Kumar Ghosh. So, we need to know that actually the key problem of the planet now. What is actually the key problem? If we consider the first and foremost difficulties for the civilization and the whole living world, that problem we can say easily it is the climate change and global warming issues. So actually the what is the cause and effect? If we want to introduce the cause and effect, the problem and its outcome, the fossil fuel actually is very essential for our developments, but it is depleting very fast. And due to the uses of fossil fuel, the carbon dioxide level, you know that it tremendously increased since last 2 decades. And at the same time, it also the problem for global warming may increase 4 degrees Celsius by the end of this century, and ultimately the sea level may raise. It's predicted that as about 6 meter it can raise. That is very troublesome for the whole living world in the universe. So that the problem energy, what is the key problem? The problem is the energy consumption trend and its type of energy uses. The global world or global energy consumption trend, if we consider, then we can see that the red mark area is the developed nations that huge consumption per capita, thus followed by the developing world, and then the least developing countries as others. But the present scenario, you know that the energy consumption actually depends on the acceleration of development. If you consider that scenario, you can see here that the scenario is a bit different now. If you consider the developed nations, China and the rest of the world, only the one country, China contribution is huge for energy consumption. So it means that pollution also huge from this country. In that consequences, if we consider the trend, we can see that here you can see that up since 2013 and afterwards, it huge actually. Red marking area actually to beyond our prediction. That means the carbon dioxide level is now is alarming in the universe, and you know due to these consequences, many areas in the world now bushfire, and it is even Amazon is also affected by the bushfire. It's considered as a lung of the earth. Amazon, it is still burning. Currently, California also burning. So think that the problem of the global warming and carbon dioxide of position on the ground of the earth. So the consideration of the carbon dioxide limit in the world now is 450 particle per million is the threshold level it considered to limit the carbon dioxide such level. We can ultimately protect the global warming to limit the temperature is 5 degrees Celsius if we can limit this level. But to do so, we need to consider some issues that the carbon dioxide production limitation to be sharply followed by China and United States. Those are mostly 50% contributor of carbon dioxide production in the current world. Then what they have to do, not only the China and United States, all other countries also have responsibilities to limit the carbon dioxide. So to do so, actually we need to limit 13.7 gigaton of reduction of carbon dioxide from the surface to get it 450 ppm scenario by 2035. So if so, then the problem or the prospect is we need to limit the fossil fuel consumption. At the same time, we need to enhance the green energy utilizations. So if so, we can see that different areas of greenhouse gas emission in here. You can see as a electrical engineering discipline consideration, we can only contribute in the power stations that almost 21% contribution of carbon dioxide or greenhouse gas emissions. So in that perspective, we can use alternative energy for electricity generations. That is the key ways or pathways to relieve this problem. So if so, the present trend of energy consumption, if we can see, you can see here that coal is the dominating energy for electricity generation, followed by oil, gas, nuclear, and renewables. But the latest scenario is that the production of hydro is almost flat because you know that it is very much natural setup. But the industrial developed renewable technology like windmill and solar photovoltaic is now progressing very fast. You can see here since 1990 it has sharply progressed and now it is in this level, is nearly the reach the hydro energy levels. And at the same time you can see here the oil or fossil energy should be limit to use. So it means that it actually enhancing the renewable technologies and while limiting the non-renewables energy consumption in electricity generations. In that sequences, you know that the developed nations already the negative impact of coal and oil, and they promote the renewable technology. And the renewables actually it focusing here. You can see that other renewables like solar, then windmills are contributing here huge for the that. In that consequences, we can see that developed nations now the scenario they are promoting the industrial developed non-hydro means solar, geothermal, and windmills productions huge. And now it is in 2019 it almost reached the same status of hydro and non-hydro contribution for renewable energy generation for electricity purpose. So if you see this scenario, you know that the windmill and solar is highly industrial favored, and there is lot of innovation in this sector to promote the energy efficiency or cost. In that sense, actually the energy demand and environmental balance is very significant. And in that scenario, the global research outcome we can see the current renewable energy generation trend. If we see from 2012 until 2040, here you can see the significant progression of renewable energy technology among the hydropower, wind, solar, geothermal, and others. But in our case, we are today going to focus on solar photovoltaic only. So we need to introduce this part. So solar, how actually solar significant? Energy, solar why it's significant because it is demanded for that to meet up the huge additional energy demand by 2030. It is clean source of energy and it has a small global warming gas and pollutant due to production of the solar photovoltaics, and it is huge actually input as solar energy, and it working environment is near environment temperature and noiseless, and the research innovation is progressing huge in this sector all over the world. And the material availability and easy transportation like the petroleum or fuel, it can easily transport from one part of the world to another part. In these consequences, The innovation of solar photovoltaics development of efficiency or energy density, whatever you can see here, you can see that the latest by 2019, how it is progressing, in this current century. It is significant actually. It is significant actually. So the solar energy, the it is actually the contribution of 52%, 52% of visible band. Then the semiconductor PN junction, and whenever light exposed on it, it actually split up the carrier and it accumulate at the two end. Ultimately, the carrier accumulation at the two end, it can produce the electric potential, and whenever it connect to the external circuit, definitely the electric current will flow. So the voltage and current ultimately produce the electric power. So how it designed in the cell, you can see here there is a emitter section at the front interface, and there is a contact at the back. So the front contact is very minor, that can allow lot of light exposure on the cell, and ultimately back contact collection of the carriers that promote the electricity that produce at the active layer. And here you can see the carrier generation and splitting at the two end, the hole and electron, and ultimately it produce against the electric potential that ultimately do the electrical performance. So in these consequences, we can see that the different materials how proficient or efficient to generate the solar electricity. Here you can see the silicon, gallium arsenide, cadmium telluride, the topmost, and indium phosphide that has the highest theoretical efficiency, you can see. And how it works, you can see here, whenever the light exposed, it transfer from low current or no current to high current due to the carrier generation by the light interaction with the solar photovoltaic materials. In this sequence, we can consider that the different cell currently available in the research laboratory and practically in the industrial applications. Those are mostly the 95% of them are contributed by silicon-based monocrystalline and polycrystalline silicons. The rest are mostly the cadmium telluride, solar thin film photovoltaics, and few of them are actually contributed by dye synthesized or organic solar cells. Then the consideration is the cost and efficiency trade-off, because the different cells actually the production cost and its practical utilization in the industry actually is challenging. So we need to trade off between the cost and efficiency to progress the industrial development or implementation in the society. So in that consequences, the levelized cost of energy and material size is very significant. Here you can see that the crystalline silicons and multicrystalline silicon, actually the energy payback time is though multicrystalline is high, but quality bit poor, but still it has a lot of industrial importance. Among the thin film photovoltaics, you can see here cadmium telluride is the most significant. That's why cadmium telluride and multicrystalline silicon actually the top most significant, that I published in this year in Optic. That what actually the significance and how it can progress the multicrystalline and cadmium telluride solar photovoltaics. Then the why the different material dissimilar contribution. You can see here that the materials actually quality and band gap is not the key consideration. You can see here the silicon, indium phosphide, gallium arsenide, cadmium telluride, all are actually written in this area with the energy available and operational energy gap is minimum. That means it can utilize significantly for the power generation. Whereas the poor quality materials that has a though significant absorption is, but it effective energy availability is very minimum, because you can see here the open circuit voltage actually depends on the part of energy band gap and also the energy loss. Actually energy loss for these low profile materials is still very high, though their band gap is high. That's why their effective energy production capability is low. So the core attention is actually how it produces the electricity in terms of current density. You can see here the materials with good crystalline quality and good properties of carrier generation ultimately possesses the top level. It has the highest current density. Then the poor quality, whatever we discussed, that higher band is it actually low current density that ultimately produce low energy densities. In that sequences, the cost and efficiency trade-off we can see here. If the materials quality is good, it should be large grain size, low defect, and low energy loss or leakage. Whereas the poor crystalline quality is low cost, low grain size, and huge leakage or the stability is bit poor. So the consideration of shift of low qualities materials possession towards the better quality fabrications technique is most significant to minimize the production cost and optimize the efficiency or energy density. In that sequence, the processing technology versus efficiency, there is some contribution of our groups. I myself leading this solar photovoltaic groups. So here you can see that the energy and efficiency propagations issues. The silicon actually based as a covalent bonding materials, followed by the 3,5 and 2,6 materials that actually has ionic properties compared to the covalent properties silicon. Then the other material like metal oxide, sulfide, telluride also contributing to generate the as a passive material, some cases active material to electricity generation as a solar photovoltaic materials. Then the nitride, phosphide, arsenide also contributing. But cells also some cases not single junction, the multi-junction aspect to cover is the huge solar spectrum, and to minimize the thermalization we can consider those technologies. In that consequences, the passivation and emitter layer fabrications in industrial approach is most significant. Here you can see that the emitter configurations at the top with the least area of metallic contact and the back with the designed and developed to passivation effect to minimize the loss at the back, and ultimately it can minimize the thickness of the active layer that ultimately reduce the production cost, and same time it can promote the efficiency. That's the industrial approach of the PRC or SIT configuration is now very auspicious or top cone uh, that work is also progressing. We are also contributing a bit on it. Then it followed by SIT technology. You know that the global warming issues is highly correlated with the thermal coefficient of the device. If we can minimize the thermal coefficient effect, it ultimately can promote the efficiency and can mitigate the thermal effect. So here you can see that the silicon is a single materials junctions can leading the loss due to the temperature coefficient effect. Whenever it make passivation with the amorphous silicon layer as a bilayer or the interlayer as heterojunction technologies, we can see it can limit the temperature coefficient that ultimately promote the efficiency and mitigate the thermal effect. That is the key direction of research to mitigate the global warming effect on the renewable technology as a solar photovoltaics. And here you can see that the data line for different materials, that how it is actually response to the temperature and irradiance, because you know that solar both temperature and irradiance act concurrently to impact on the energy efficiency or performance of the solar photovoltaic. So in case of those, you can see here the different materials has a negative temperature coefficient, means it can reduce the voltage and efficiency with the temperature effect. But if we compare with the silicon and crystalline and multicrystalline, the amorphous case, you can see band gap is huge and also the temperature coefficient effect is minimum. So in that case, if we introduce such type of higher band gap transparent material as emitter as a heterojunction configuration, we can minimize the temperature coefficient effect, and that ultimately implement here an eminent professor from Japan, Kanka technology, that SIT technology they invented as about 8 years back. So we are also working in it. Then advanced silicon nanowire for the emitter to promote the absorption and to enhance the electrical performance. We are working also here. You can see that the different bandages it can support by the different crystalline property that can ultimately promote the current density of the solar photovoltaics. We already published it in a review paper. Then the different interlayer or different passivation contact for the silicon technology, you can see here we're using different metal oxide as a TM transparent conduct TCM transparent conducting materials that actually promote the uh, light absorption to the active material. At the same time it can act as a passivation or to minimize the band gap absorption, or it can actually uh, do the band gap reflection that ultimately limit the thermal inclusion in the solar photovoltaic in the global warming scenario. So you can see different materials utilized on the silicon technology has a different responsibility. You can see that the highest is the silicon dioxide and silicon nitride materials in different configuration. And ultimately we also published it in renewable sustainable energy reviews. And then the different junctions with different density of doping concentrations can also promote or make variation of responsivity. You can see here with the different configurations like PN, P plus, N, P plus ion, and that ultimately make variation of responsivity. Responsivity is nothing but the optical absorption as input and the electrical performance at the output, how it is actually. Those configuration, the responsivity is higher, definitely their conversion rate of optical to electrical is higher. In that consequence, you can see different configuration and you can justify the different responsivity, and it can be chosen that which configuration is best for highest responsivity. At the same time, you can analyze that where the junction should be effective to make effective solar photovoltaic with the absorption edge. Here you can see that P plus IN, P plus N and PN had different depth of the PN junction that also made variation with the different doping concentration. Ultimately, it is very significant background work to develop the high efficient solar photovoltaic. So then the efficiency progression issues, the advancement of heterojunction and multi-junction concept also is there. In this perspective, we actually working on the indium gallium nitride on silicon as a simulation work, because you know that indium gallium nitride can cover huge solar spectrum and ultimately it can promote the current density. At the same time, the series configuration of cell can promote the open circuit voltage, and that may be very useful for solar photovoltaic applications. Actually, in my work in a PhD in Japan, I did the background work on gallium nitride fabrication on silicon. Here is the methodology how we did it. You can see it in a short review that using the different interface material, we fabricated gallium nitride on silicon. We used the gallium arsenide porous layer converted into gallium nitride to produce gallium nitride EP layer on silicon, and it was also published in 2003 the Q1 journal. Then the fabrication technique you can see here, and the interface property, uh, structural property, and the atomic layout of the gallium nitride. You can see here very sharp peak of the R heat that is very well arranged of the EP layer of gallium nitride on silicon using the porous interface layer. You can see here, this is gallium nitride, this is silicon, this is the interface gallium nitride porous layer, and this is the surface. So here you can see that the energy peak of the lower higher edge energies can distinguish the atomic arrangement or stress level, and different gas uses the concept of the materials quality development you can realize from this figure. and then ultimately the uh, EP layers excitonic level can reveal that the uh, stress effect that is very significant for optoelectrical design. How minimize the stress of the EP layer that can promote the electrical properties or optical properties. So you can see here that the different configuration had made different stress level with the gallium nitride on silicon. So then we also use silicon carbide interface layer to produce gallium nitride EP layer on silicon. This is the interface, sorry, the surface of the gallium nitride. You can see different defect of the interface because the silicon carbide is very difficult to generate on the silicon that can ultimately make a uh, defective layers. But ultimately you can see that different IP layer with different interface can shift the near band speaks. Ultimately it can reveal that different um, stress level or different optical effect of the materials. So you can more details can see here that how the carrier gas effect on the production of the EP layers stress and its quality, and different excitonic peak fluid half maximum can reveal the different quality. Wherever it is less, that is the best qualities gallium nitride produced on silicon. Actually it is also published. Then the gallium nitride on silicon heterojunction and multi-junction technology, we also published it in our review. You can see here that the higher edge of the solar spectrum cannot cover by silicon. So if we can introduce the higher bandage material, it definitely can cover and it can extend the open circuit voltage. So in that case, it can promote the efficiency, because efficiency promotion ultimately it will promote the solar photovoltaic in the society, and that will be very effective to limit the carbon emission and global warming issues. So in that perspective, we designed the indium gallium nitride cell on silicon, and there is no hurdle or barrier that can make series configuration with the top cell and bottom silicon cell, and ultimately it can configure that the higher open circuit voltage by indium gallium nitride and lower open circuit voltage by the silicon technology can promote the open circuit voltage. At the same time it can make the series configuration to promote the current density that ultimately promote the efficiency. So in these consequences we can see here that the silicon, you can see the dip velocity of silicon is very less compared to the gallium nitride and indium nitride. Whenever we fabricate the gallium nitride indium nitride composite indium gallium nitride, that ultimately shift the dip velocity or ultimately shift the current density. You know that the electrical configuration, whenever a system open circuit voltage is high, definitely the short circuit current density must be low, because open circuit and short circuit is the trade-off between the voltage and current. In that sequences, if we can promote the open circuit voltage at the same time can promote the current density, that will be more beneficial for efficiency progression. You can see here that the shift of the current density due to indium gallium nitride introductions on the silicons can ultimately promote the energy efficiency. And you can see here that the effect of the utilization of indium gallium nitride is very significant in compared to the crystalline silicons. So in that perspective, if we consider the different interlayer for introduction of the indium gallium nitride on silicon, we also published it in a journal that shows the no interlayer, the aluminum nitride and silicon dioxide interlayer is more significant to get it the current density uniformity. It is a certain depth of the junctions, and that promote the energy efficiency of the indium gallium nitride cell on silicon. And different composition of indium in gallium nitride can promote different open circuit voltage, and ultimately it can make variation of current density. If we can intend to make get a open circuit voltage, ultimately we need to sacrifice the lower short circuit current density. In this trade-off between VOC and JSC, you can fix certain level that can be optimize the power conversion efficiency. So then ultimately the different interlayer impact on the indium gallium nitride fabrication on silicon, that is actually the simulation work. You can see here that the relationship between the uh, it is actually not to the due to the permittivity effect, is definitely the interface materials in plane lattice mismatch effect is very significant, that can actually make variation of the interlayer effect on the efficiency of indium gallium nitrides. So the low cost solar cell technology we also introduced, that hybrid organic inorganic solar cell technology, because it is very significant to minimize the emitter layer development in heterojunction, utilizing lower profile fabrication process or low temperature budget or low carbon budget. So it should be definitely more effective to minimize the interface defect and leakage current at the interface. That should be more effective for development of organic inorganic hybrid solar cell. You can see here we also published the organic material different configuration to promote the efficiency or open circuit voltage of solar photovoltaics. We also already published it. And then the different interlayer that introduced for the whole transport or electron transport layer for the organic or inorganic materials as solar cell. Here you can see that different bands can support for different activation energy, different work function, that ultimately can make variation of carrier conductions. And then the thermoelectric concept, if we consider that solar photovoltaic not only optoelectric concept, there is a thermoelectric concept also. So here you can see that the balance between the thermal and electrical conductivity is very significant to utilize those materials for interlayers fabrication. In that prospect, you can see here the zinc oxide, titanium dioxide and tin oxide is very significant, that balance between thermal and electrical conductivity, that ultimately promote the electrical efficiency of third generation or emerging solar cells technologies. So you can also did some simulation work on third generation solar photovoltaic fabrications. Here is the open circuit voltage and the layout of the design. You can see here the using the RF spattering and the uh, the pyrolysis method growth process of PTA on the zinc oxide materials. This is the surface property, and then the surface property you can see here is not so bad using the very low profile fabrication process. So the optoelectrical characterization, you can see that the emitter layer is highly transparent, that is more beneficial to absorb the uh, light in the active material and junctions, and that ultimately promote the transparent solar photovoltaic development, that is very potential for house applications of solar photovoltaics and in-house application as well. You can see here the band is very huge and it is almost transparent for the absorption of solar band, and that definitely can make the excitonic energy transformation from optical to electrical. And here you can see that the different growth properties that promote the different uh, current density with the different applications of voltage, and definitely ultimately it can make the uh, forward and reverse current ratio, that is the very essential for to determine the junction property of PN junctions, and the grain size of the materials, how significant to make the barrier height, and ultimately the grain size impact on the leakage current. We can see here that is more significant for the analysis of the materials. How is the growth property suitable for develop the low leakage current heterojunction. Ultimately, we published it in a electron materials letter in Springer just the years 3 months back. And here you can see that the rectifying ratio and the current density and leakage current. That leakage current standard is very minimum compared to the inorganic heterojunction, but here is the organic inorganic heterojunction that minimized because low temperature deposition actually minimize the interface defect, and that ultimately promote the